Good morning, everybody. Today I would like to solve this structural analysis problem with you. This is, as we can see here, this is a frame structure which is subjected to a lateral load P, and all the parameters such as the Jones modulus, the moment of inertia, the area are shown below, as well as the geometry of the frame structure. The peculiar of this problem is that beam has two lead end zones. In this case, the beta ratio is equal to 0.05 of the total length of the structure. In this case, LT is equal to 3.6 times the length of the value of L. To solve this problem, I developed a MATLAB code using the stiffness matrix approach, and we will compare the results in terms of displacement for end forces with those given by the structural commercial software, such as in this case I am using SAP 2000. Okay, let's do it. First of all, I will explain about how the code works. And at the beginning, you need to input the number of the nodes that we have. In this case, we know that we have only four nodes. Then you need to input the x and y coordinate of each node. Then after that, a number of elements. In this case, yes, we have three elements, as well as the initial and the final node of each element. Mm, These vector x and y are storing the coordinate of each node to draw or to plot the undeformed shape of the structure. Okay, after that we need to input the area of each element, the Jones modulus of each element, as well as the moment of inertia. Plotting the undeformed structure in this case is a frame structure. Knowing the x and y vectors, we can plot the undeformed shape of the structure. The code by itself will calculate the length and the cosine and sine of the angle that element will form with the x-axis. We need to define the rotational transformation matrix in order to have in order to convert the local stiffness matrix to the global stiffness matrix. And after that, we need to input how many elements have a read and zones. In this case, only we have one element that is the beam, and we need to input the length of the read and zones. And for the element that have a read and zone, we need to calculate how the code will calculate the read and zone transformation matrix. And for those that don't have read and zone, the read and zone transformation matrix will take the value of the identity matrix. After that, we need to define the local stiffness matrix, KL. We recall these are this matrix is already defined using the Jones modulus, the area, and the length of the element. In this case, another thing that I want to point out here is that we are considering a 6 degree of freedom for elements, two rotationals and two rotationals and two translationals and one rotational for each node. That in total are 6 degree of freedom. And after that, we will calculate the global the stiffness matrix in the global coordinate system. We are doing this in order to assembly the global stiffness matrix. So maybe it's important to notice what means K bar and what means only K, using the rotational transformation matrix and the read and zone transformation matrix that we defined previously. So let me explain here. So we have, for example, these elements, no, that form a phi angle with the x-axis, and for this element we define the stiffness local stiffness matrix using this the degree of freedom along the length of the element. No? So we are using this 6 degree of freedom. But in order to have the same coordinate system, we need to transform this degree of freedom in the global coordinate system. So once we use the transformational the rotational transformation matrix, T rotational, we will have these ones, this new degree of freedom. That in this case we are those are called 1 bar, 2 bar, 3 bar, 4, 5, and 6. Okay, that would be the end of the problem if we don't consider the read and sums. But for this case, we are let me change the color. We are considered the read and sums at the end of the elements. Um, to take into account these read and sums, we need to multiply by the read and sums transformation matrix to have the new we will have the new degree of freedom or the new stiffness matrix, but considering in the global coordinate system, considering these read and sums. Why? That is why we need to define the rotational transformation matrix and the read and sum transformation matrix. Okay, so um, continue with this with this explanation of the code. We need to the code will calculate the degree of freedom tag. We are considering 3 degree of freedom by node, so the total degree of freedom tag is 3 times the number of nodes. The ID, we will use the ID array approach, and this is in the same way that all the commercial software works. So we need to say we need to consider the constraints in for example, at the supports, no? When we have 0 degree of freedom, because in our case, for example, we have a fixed support, so the degree of freedom, the element doesn't have the translation and rotation in that in that fixed end. So the idea, we need to input the ID, which is the real degree of freedom of the structure, and we need to as well relate the degree of freedom of each element to the degree of freedom tag of the global structure. We will see in detail when we solve when we will input the data. Relating the degree of freedom of each element to the global degree of freedom of the structure, we can assemble. No? And this is the part in that we assemble the global stiffness matrix. After that, we input the force and we solve the displacement using the equation, the inverse of the stiffness matrix multiplied by the vector force that we already input here. And we can do the extractions basis on this degree of freedom of the global structure. We can determine the displacement and rotation at the end of each element. And after that, we can solve. We can as well. We can use the use of the rotational and the transformation matrix to determine the local displacement of each element, and we can just using the same equation, the force vector is equal to the stiffness matrix times the displacement at the ends of the nodes. As well, we already know what means F bar, right, is the end forces in the deformable part of the beam, and EL are the end forces considered in the rigid end zones. Okay, for horizontal elements, the local forces need to be equal to the bar forces because we are using the same coordinate system, and the rotational transformation matrix is equal to the identity. So once we determine the end displacements and rotations, we can use the governing equation of a beam to to calculate the deformed shape of the structure using, for example, these equations. And to draw in MATLAB, we will use the rotational and translational um, co coordinate system to draw using the same frame of coordinate system. This is, for example, for the beam, and as well for the column or for the column 2 and the column number 3. And after that, just need to plot. So just recalling, uh, we can draw the form shape of the structure knowing the end displacements and rotation of each element using the governing equation, because these ones will be the new boundary conditions to determine the function, right? To determine the deflection function of each element. So um, this is the end of the code. This will be available in the comments. So let's do it. So you can run the code, change the folder here, as well, right? Enter the number of nodes. So first we can number the nodes. In this case, I will use this numbering. This is number 1, number 2, number 3, and this will be the number 4. Okay, it will be my first element, my second element, and my third element. So the number of nodes that the code asks me is 4. We need to enter as we said, we need to enter the coordinate of each node. The first node is if we locate our coordinate system here in the node C, X and Y, we can see that for the first node, the coordinate X is equal to 0, Y is equal to 0, and for the second node is 3.6 times L. We will use inches in length, so 3.6 10 foot is equal to 432 inches, and is 0 here. And for the third node, is the x coordinate is equal to 0 and 180 in height, and the other one for the fourth node is 432 and 180. And the number of elements, as we can see here, are only 3 elements. And we need to relate. We need to input the initial node for the first and the initial and the final node for each element. So the initial node for the first element, as we can see, is the number 3 node, and number 4 the final, and for the second element is the number 1 and number 3, and for the 3 elements we have the number 2 and number 4 as initial and final nodes. The code asks me to enter the area of the first element. In this case is 1000 inch square. The second elements are as the same to the third element, is 30,396. 30,396. The Jones modulus is the same for all the elements, is 4,757 for 4757 for each element. The moment of inertia for the being, which is our first element, is 11,295. 11,295. Um, for the moment of inertia of the column is like a 21,500,000, right? So it's 21,500,000, 3 zeros here, as the same for the other elements. Okay, so once we determine this, the code will ask, and we plot the undeformed shape of the structure. Is 0 here, and 400, um, the geometry of the undeformed shape of the structure, right? And after that says enter the number of elements we read and so on. As we can see in the problem statement, we only have one element. So we said it's the bin, right? So one element, and element has written so. The element one has a written so, yes. What is the dimension of the written zone? If we multiply 0.05 by the total length, we will determine that this value is 21.6. It's a vector, right? In the x direction, have this 21.6 at the beginning, and the dimension of the written zone in the y direction is equal to 0. And for the second written zone, that is at the end of the element, is a vector. It needs to be at 21.6. And as the same, we have only horizontal written zone, so this value is equal to 0. The element 2 has written zone. We need we can say is no, as the same to the third element. Okay, so enter the real degree of freedom of the structure, which corresponds to the degree of freedom tag. Yeah, we are saying the degree of freedom tag because we are using the idea right approach, that we are considering 3 degree of freedom by node, right? So I am drawing the degree of freedom tag for each node, and then 9, in this case will be 10, 11, 12. Okay, these are all the degree of freedom for the structure, but the idea degree of freedom consider only considering the constraints, because we are having here fixed supports. All of these degree of freedoms are equal to 0 because they cannot rotate, and they cannot translate. So we will say that this node we only have actually 1, 2, and 3 degree of freedom, and it is not as well, no? 4, 5, and 6. All of these are the degree of freedom. Mm, the real degree of, we can say that those are the real degree of freedom, real considering the constraints that we have in the supports. So when the code asks us enter the real degree of freedom of the structure will correspond to the degree of freedom tag, we can say from 1 to 6 are 0 because they cannot move and rotate. So we enter 0 here. And for the 7th degree of freedom tag correspond to the first degree of freedom of the structure, right? And the 8, and then the 9 to the 3, and the 10 to the 4, 5, and 6. So we already input the degree of freedom, the real degree of freedom of the structure, and the code as the degree of freedom tag to which corresponds to the first degree of freedom of the first element. We need to input that in order to assembly, right? To relate the degree of freedom of each element to the degree of freedom of the structure. So uh, the element, as we can see here, each element only has six degree of freedom, right? So for the first element, for the being, we have this degree of freedom in the global coordinate system. So we can say the first degree of freedom corresponds to the 7th degree of freedom tag, and the second degree of freedom of the element corresponds to the 8th degree of freedom tag of the structure, and the third degree of freedom corresponds to the 9th degree of freedom tag of the structure. Following the same procedure, we can figure it out that the 4 correspond to the 13th degree of freedom tag, and the 5 and the 6 correspond to the 12th degree of freedom tag. No? So says no degree of freedom of each degree of freedom tag which corresponds to that first degree of freedom. In this case is 7th and 9th. No? 7 to the second is 8, to the third one is 9, for the fourth is 10th, 11th, and 12th. This is for the first element. And for the second element, we have for the second element is a column. So as we can see, the first degree of freedom corresponds to the first degree of freedom tag. 1, 2, 3. At the end, we have 7th, 8th, 9th, right? 7th, 8th, 9th. And for the third element, we have 4, 5, 6. 4, 5, 6, and 10, 11, and 12, right? 10, 11, and 12 degree of freedom tag, which correspond to the degree of freedom of each element. Now we need to enter the forces. We only need to see the graph, and we realize that only have a force in the first degree of freedom, and the other is equal to 0, and the value is 100 kips. So 100 kips in the first degree of freedom and 0 in the other one, right? Okay, so doing that, first of all, we can plot the graph of the we can plot the graph of the deformed shape of the structure, and these are read and songs here, and we will compare the results that MATLAB is giving us with the SAP 2000 software. This is the 2000 software. To just a quick review, we define the materials using this material. That we are not considering the weight of each element, but we are considering the Jones modulus. No? Okay. After that, we define the frame elements. For example, the column, right? I define this section in order to have the same moment of inertia, and I will modify the cross section area, the factor, no, the multiplication factor, in order to have the same. Because when we already define this section, we already have the cross section area, right? So, but in order to have the same as the problem statement, just we need to calculate the ratio and put it here. And we are not considering the shear deformation. We are not using a Timoshenko beam. We just following the Euler-Belori beam theory. And for these values need to be big values in order to not consider the shear deformation. And the same as the beam, right? We defined in order to have the same moment of inertia, and we will modify the multiplication factor for the area and for the shear deformation. As well, in order to define the read and so on in SAP, we just select the beam, assigned frame, read, and end length offset. And we need to put here, no, 20. In this case, will be 20.6 at the end, and 20.6 at the beginning and at the end. And we need to put a retention factor equal to 1 to consider the total length that we are introducing here. I already done that, and we can see here, no, 21.6 of the read end zones at the end of this beam. And after that, we need to put the concentrate load, the concentrate lateral load here is equal to 100, and run the code, right? Already are defined, and we just need to run the code. As we can see, if we compare first the deformed shape of the structure with the deformed shape of that MATLAB that our code is given, it's almost the same, right? So in this case, the retention zone is only a straight line here at the end, and at the beginning and the end of the beam. Okay, so now we need to as well, we can say that the translation and rotation of the ends of the elements, right? So uh, MATLAB first, when we solve the problem, as a result, they will give us, for example, that that would be mm, at the end of the element. Okay, so for example, in this case, the displacement, we are here. The MATLAB is okay. Let me see first. Okay, this is the displacement and rotation for the global structure. As we can see, um, the translation is equal to 0.016 inches. That is the in our graph is this translation. No? These are the 6 degree of freedom that we are considering for the global structure. This, the translation have a positive translation to the right, to the 0.016 inches. Um, Almost nothing in the vertical translation, and this is a rotational that the MATLAB is giving us, and in the it's almost zero here, and for the end of the for this degree of freedom, for the 4 degree of freedom, we will have a 0.003 and almost zero in the other ones, right? So we compare the results with the value here is, as you can see, 0.016, almost zero in the other degree of freedom. And here we can say the value of 0.003 in the translation, and rotation is almost equal to zero. That we are comparing the results, and we can say that are very close results. Now to check the forces that are important to draw the shear diagram and the moment diagram and the axial diagram, we can we can follow the forces in the local coordinate system, right? So this is for the first element, for the second element, and for the third element. No? For example, as we can see in the beam has uh, for for the beam, this is the third degree of freedom that which correspond to the moment. It's as minus 0.0009 and minus 0.006 at as value of at the end of the beam. So when we just can say, show me the moments here, are very these values, no? 9.6, 9 kip times inch at the initial and 0.06, right? Almost at the end of the beam. For the column, for example, we can say this is the biggest one. It's like 15,000. And for the column here, we can say that this is a value, no? Times 15,000, no? Multiplied by 10 to the fourth, 1.5 times to the 10 to the fourth. And at the end, we can is around tenths, right? So we can say here, and it's minus 9.6. Okay, for the shear forces, we can say the second degree of freedom. We can see the second degree of freedom here is 84 and 84 here, which correspond to the forces here, no? Around 85 that are almost the same. And for the third column, we can follow the same procedure, and we can find the moments at the end, right? The shear are constants, for that means that the moments are have a linear variation. For example, at the beginning we have around 2,608, and this is the value right here that we are considering. It's almost the same. And here is 6.5. It's almost 7, right? The shear forces are almost here is 16. No, it's for 14.75. I mean, we can have some difference because the moment of inertia is calculated by the section that I just uh, introduced to the SAP. No? But in general, the results are almost the same. Okay, so this is what I want to show here. This is how the software works indeed. And in this code, we can use this code as well to solve different kinds of a structure. Just we need to input correctly the number of nodes, the number of elements that we have the coordinate system, and the the Jones parameters such as the Jones modulus, the area, and the moment of inertia. Well, I hope that this can be helpful for you. And I use the same code in the next video to solve a 20-story buildings with a lateral load. Okay, thank you for watching. That's it for me.